Let me present PhD student Polina Panteleeva with the talk Feynman formula that maybe provides a solution to a generalized Black-Scholes equation. Polina, you have 25 minutes for talk and 5 minutes for questions. You are welcome.
Thank you. I will tell you about Feynman formula that maybe provides a solution to a generalized Black-Scholes equation. I have a big problem with, okay, it works. So this is a talk on the research that is only in the very beginning of it. So there will be no proved theorems. There will be ideas and problem settings. There will be a formula that we wish to prove to be a solution of a generalized Black-Scholes equation. And this is my second in life talk in English, so your kind support is appreciated. The central theorem that we use in our work is Chernoff theorem. Suppose that the following three conditions are met. The first one, that C0 semigroup with generator L is in Banach space F is given. There exists a strongly continuous mapping S, such that S of 0 is identity operator, and the inequality, the norm of S of t is less or equal of e in the power of wt holds for all positive t. And the third one, there exists a dense linear subspace D in F, such that for all functions F in D, there exists a limit. Moreover, S prime of 0 on D has a closure that coincides with the generator L. Then, if all three conditions holds, then the following statement holds too. For every F in Banach space, as n tends to infinity, we have such an approximation tends to the semigroup locally uniformly with respect to time. It means that for each t capital greater than 0 and each F from Banach space, we have such a formula. Let C0 semigroup with generator L in Banach space F be given. The mapping S is called a Chernoff function. Chernoff function for operator L, if and only if it satisfies the condition C of Chernoff theorem above, and in this case, expression S of t over n in the power of n are called Chernoff approximations to the semigroup E in the power of TL. Okay. Consider a Cauchy problem for the equation with constant coefficients, and let's define operator H by this rule. For all x, for all real x and all f from some dense subspace of appropriate Banach space of functions, real valued f, let us introduce function valued function u by this rule. Then the above Cauchy problem can be rewritten as follows. If H is the generator of C0 semigroup in the space of functions that be working, then the solution of both Cauchy problems are given by the so-called heat semigroup that provides by this formula. Now consider Cauchy problem for the heat equation with variable coefficients, coefficient A. And let's define operator HV by this rule for all x in R and all f from some dense subspace of appropriate Banach space of functions. Let us introduce function valued function u by this rule, and then the above Cauchy problem also can be rewritten as follows. As before, the solution is given by the semigroup, but the analog of previous formula does not give the semigroup anymore. Operator valued function S does not possess the semigroup property. It means that we should not expect that S of T1 plus T2 is equal to composition of S of T1 and S of T2. And that E in the power of TH B is not equal to S of T. But this function S is still useful for the following reason. Under certain conditions, it is known that the semigroup is given in the form. This is a very particular case of what is written in the paper of both Kograt-House and Smolyanov. And now we are coming to the main topic of the talk. Our plan is to consider the Black-Scholes equation and do with it exactly what was done with the heat equation above. Consider linear differential operator A given by this. If operator A generates a C0 semigroup, then Cauchy problem for parabolic equation looks like this and has solution U that provides by C0 semigroup. Moreover, for each capital T greater than 0, Cauchy problem for parabolic equation is following. Has solution represented by this formula. Note that 3 becomes the Black-Scholes equation for option pricing if we use the following notation. V is the price of the option is a function of stock price X and time T A of X is equal to this with sigma greater than 0 and B of X is equal to this and C is like this. So the operator L, defined as follows, is an unbounded operator in such Banach space with respect to this norm. S and tau here are positive constants. In the case of constant parameters sigma and R, the solution to the Cauchy problem for the Black-Scholes equation with U greater than 0 is given. For example, it is in Goldstein papers and in Goldstein-Minini-Romanelli paper, and they give it by this formula. But what if the coefficients sigma and R are not constants, but are bounded, continuous, and positive functions? So in this case, let's just do it like before. Let's put here R of X and sigma of X. It is the same formula as here, but we just replace the constant coefficients to the functions. So if this S is a Chernoff function, then Chernoff approximations will be following. So our plan is to prove that this function S is a Chernoff function. It means that we have to show that all the conditions of Chernoff theorem hold. And it's all for now. So thank you for your attention.
Thank you, Polina. Okay, now is the time for the questions. Please put your questions. If there are no questions, then according to the scheduler, from 1440 to 15, we have a technical break.